I'm starting off again with vapor phase deposition process, and now I would be bringing in plasma deposition processes. Now, here on NPTEL, you have got this excellent lecture which is on plasma deposition process. This was developed mainly to cover VLSI design. This particular lecture for VLSI design, and you can review it for additional information as applied to semiconductor technology. Now, this video shows you a simulation of CVD process. The vapors are coming in, they are being deposited on a surface, and the surface gets coated progressively. This is the fundamental main thing of vapor deposition process. The spatial distribution, as you see, is given over here, and the coverage on the substrate is first the center part gets covered and then progressively the outer parts get covered, and hence the deposition thickness varies just as, wait, let me freeze it, and the deposition thickness varies like this. So, in the center part, the deposit thickness is much higher than in the outer part. Now, while going through this, I found a very interesting one, something I will pick up and you can look at it later, is this laser deposition technology. This will also serve as an useful adjunct to how laser assisted depositions are done. Now, CVD can be broken up into many parts. One is the thermal CVD reactors. Where what you have is a reactor. Normally it's made up of quartz. The substrates are kept here. On a stand, and these are I have drawn in resistance heaters. The gas comes in through here. There's a pressure gauge, and the exhaust is taken out from here. Now, here one of the problems is, because the resistance heaters are on the surface of the reactors, the walls will also get heated. So, we have a coating on the walls also, and if we are going to use this hot wall reactor, we lose a significant amount of the material to be coated to the walls. The difficulty is, what happens over here is, these substrates are coated, they are taken away and a new bunch comes in. Because it is a hot wall reactor, the thickness of the deposits on the walls keep on increasing. And finally, they flake. Flake is like the paint which peels off, that flake. Now, this flake can contaminate the coatings over here. That's a major problem of the hot wall reactor. This can be avoided by using a cold wall reactor. In this reactor, instead of the resistance heaters, we have got induction heating. So that the gases and the substrates, they are the ones which get heated. This is, let us say, quartz tube. These are the substrates. The quartz tubes will not get heated. As a result, the coating forms only on the substrates and not anywhere else. Hence, the system remains very clean and we get coatings on this. Here you have to understand that the decomposition occurs only on the substrate surface, because that is the only part which has been heated by the induction heater. The difficulty is this, that we have at times a problem that the deposition rates are very low, because here it's a very slow process, and hence what we have is very slow deposition of the coatings. Now, they may not be all that bad, because then I have got an uniform dense coating. Now, let me come to what is plasma enhanced CVD. Plasma enhanced CVD. You see, let us say we have got a substrate. This was the substrate on which I want a thin coating. Whether I am using HVOF spray or a CVD reactor, there will always be a thermal expansion mismatch between the substrate and what I have coated on it. If this mismatch proves to be a big problem, if during deposition the temperature rises, as I said, for HVOF temperature goes to only 400 degrees centigrade, not much. degun 50, 60 degrees centigrade at most. But in a CVD reactor, the temperature shoots up to the temperature of the furnace. And as a result, one of the biggest problems happens is if there is thermal mismatch, the whole thing is lost. The coating may peel off, the coating may be under strain, and hence there might be strains in the film which might later lead to failure. So, the goal has always been to have a deposition process where the substrate does not heat up much, and even if the lattices are not matched, the coating does not fall off. In plasma enhanced CVD, before I go in the details, I would like to state that the temperatures of the substrate and the coating, if I am doing say a CVD of silicon nitride coating, temperature of substrate would be anywhere near 900 degrees centigrade. Whereas in the PECVD, this is hardly 200 degrees centigrade. The problem here is the substrate will expand, deposit will form, substrate cooled to room temperature, and here comes a big problem. If the substrate has expanded significantly, like take any metal, what would happen? The thermal expansion coefficient of the ceramic is much lower than that of the substrate. So, as the coating gets thick, say 10 micrometer, the coating peels off. So, in these cases, if we have to work with, we have to work with a system where the temperature of deposition does not exceed 200 degree, 100 degree when we are talking of metallization of plastics. This is the advantage of plasma enhanced CVD. In plasma, and what is a, now everyone, I have talked of plasma quite a few times. What are these plasmas? These plasmas are ionized gases consisting of electrons and ions. Electrons are the primary charge carriers in the plasma. You had seen that yesterday when I was talking of DC, there's RF magnetron sputtering, is RF magnetron sputtering. So, if I have to have, let us say, going back to, say this is a substrate, this is the, or rather the gases are coming in, if the substrate is immersed in the plasma, it may get hot. How can I help improve the plasma formation? Like yesterday, I used a radio frequency, RF. Here in plasma CVD reactors, what we have fundamentally are, I'll go through that example later, is the ions have got very, very low energies. They inelastically collide with gas molecules. What happens is this, that I have got a substrate this is the sheath. Remember the glow sheath that you saw elsewhere? This is the boundary layer. And here is the entire plasma. What can happen? The neutral particles can come and hit the substrate. They will come by a diffusion linked process. If there are ionic species, they will also come and hit the substrate. Here I have the advantage that I will have the ionic species accelerating so that they come and hit with a significant force. In both the cases, what is very important is that the sticking coefficient is very high. That is, the vapors come and stick on the surface. Finally, the reactant products go out. So, if I draw a typical diagram of a CVD reactor, what will I have is a closed chamber where I shall have say the substrates, these are the heaters over here. The gases are pumped through centrally, and the whole thing is put in a vacuum tight chamber. So the gases go in, the gases go out, they react with these wafers or substances, they work on by forming the corresponding compound on the surface. In this case, we can use various types of organics which vaporize easily, burn cleanly leaving no carbon particles behind. This is a basic building block of a plasma enhanced CVD. I'm still talking of generalities. I'll go to an in-depth understanding of plasma enhanced CVDs by the end when the class is up. Another very interesting deposition technology which I had shown you on the terminal was laser assisted deposition. Here what you have is what do I, okay, let me put in a laser beam through here. This is the substrate. The gas is being fed through here. The laser beam would cause photo dissociation of the reactant, giving you a coating on the substrate surface. I showed you a slide or just now a video on YouTube where they have talked of laser assisted deposition. This laser assisted deposition is also an industry standard today. You have to decide what is the material you want to deposit. If you wish to deposit Si3N4 on the surface, I would start off by taking TEOS, tetraethyl orthosilicate, plus I would take tetraethyl orthosilicate and ammonia. The silicon in TEOS would react with the ammonia, giving you the hard Si3N4 coating. These coatings, this type of coatings are very useful in biomedical application. Now let me explore the PECVD a little more. I had stated that the vapor has to come into contact with the surface which is heated. Other parts of the whatever you have got in the tube as suspenders, etc., they don't. How to make it happen? For example, let me take the case of semiconductor industry, where they want to continuously coat silicon with these materials. Uh, what do I do? Okay. Let me rely more on VLSI. That's the easiest part. This is a silicon wafer. Here, these are active areas where the silicon wafer has got circuits or whatever. It is in this particular area, which are called vias, do I want to fill it in with an insulating layer. And let's presume it is Si3 and 4, though any semiconductor person would simply kill me if I say this, that I want this Si3 and 4 in that fashion. So I would have to place heaters over here just beneath nitrogen is used for purging the process gas. This will come and deposit only on this via. It may also deposit here, but all these surfaces are coated, which can be removed. And in this particular process, which is called atmosphere pressure CVD, we do have problems of uniform deposition. To counter it, we have got now low pressure CVD. In low pressure CVD, we have got a quartz tube along which heating coils are placed. This is a quartz tube. These are the wafers. And the process gas flows through in this way, thus coating the substrates by reaction of the process gas, which can be, as I said, tetraethyl orthosilicate plus ammonia, to give you silicon dioxide, which will fall on this surface. And if I have got vias like this, they would only coat something over here. So this is LPCVD. Another technique which is coming out is ALD, atomic layer deposition. In this particular design, what we have is this is the substrate. The vapor pulses are pushed through here. This is the heater, inductively coupled heater, and they reside on the heated substrate, leave behind a deposition layer, and then it is pumped out. Now, ALD, atomic layer, depositing this by plasma enhanced chemical vapor deposition is very difficult, because when I am talking of atomic layer deposition means I want to deposit the atoms atom by atom. And hence, we have to reduce a lot of other parameters if this atomic layer deposition unit has to work. Though using this method, films were drawn at different places in India, and it was found that the vacuum has the biggest role to play over here. Now, this plasma enhanced vapor deposition is a very, very interesting technique, because the deposition takes place inside the glow plasma, and no PECVD. That's what I was afraid of. I'm not getting it. Ignore it. It is simply not there. Let's see what is happening here. This is all that I get. Anyway, let's drop this. So, in plasma enhanced CVD, one of the biggest advantages is the substrate can be maintained at very low temperature. Let us look at the systems that can be that have been deposited by PECVD. Si3N4 silicon nitride, SiO. A lot of people will be shaken with SiO, but it exists. SiO2, SiAlON, diamond like carbon, amorphous silicon, polysilicon. These are amongst the many industrial products that have been found. Now, let me show you an interesting technology for accelerating plasma enhanced chemical vapor deposition. This is the reaction chamber through which we pass in silane, and through this end we pass in N2O. Our goal is to get silicon nitride. What is done is this is earthed, this is earthed, the whole thing is earthed, and I have got a sheath which is earthed over here. In this case, the plasma volume will cover this whole area, and the advantage is here I have put in an RF frequency of 13.56 megahertz, and here I have got a lower frequency of 360 megahertz or 360 hertz, sorry, hertz, kilohertz. In such a case, I will have a silicon nitride plasma on the substrate at room temperature itself, and a very hard adherent coating of silicon nitride. We could additionally use here, this is called basically a triode arrangement. Like a triode valves which you have not seen is triode arrangement. Advantage, lower temperature, very little strain, and as a result very good adherent thin film. This triode technology is just coming into the market, and it will be some time before it is commercialized. But this triode method gives us the ability to have very, very thin films with very high bonding. I would rather not proceed any further because this is not a course on thin film coatings, but I would like to summarize the different methods of coating that I have covered. I have used alkoxides based sol gel coatings. In alkoxide based sol gel coatings, I had done two types of coatings. Alkoxide based sol gel coatings has its advantages and disadvantages. The disadvantages which frequently prevent us from using the process is that the hydrolysis rates in case of multi-component coatings, they are never equal. And it becomes very hard at times to match the hydrolysis rates. That is one problem. But however, if the hydrolysis rates can be matched, then the alkoxide route gives us unprecedented power to modify the composition of the film and look at various properties which it may be used for. The second method I had talked of coatings was when I talked of thermal spray pyrolysis. Thermal spray pyrolysis has given coatings or powder sizes which are in the 30 to 40 to 50 nanometer range, something most cannot develop. And then I had gone over to physical vapor deposition processes like RF magnetron sputtering specifically for ceramics, and of course the other coatings in that, the thin film coatings, coating from solution, all those are there. You can use that. Then came the high velocity oxygen fuel spray, and there we saw that HVF fuel spray coating is being used industrially for cleaning up the surface and making the surface smoother so that it can be used. Then came the detonation gun coating, where I talked of the detonation gun depositing ultra thin coatings at temperatures where plastics do not soften. I had talked of the thermal CVD, the hot wall reactor method, and went on to say that the hot wall reactor method has its own problems, because unless you change the reactor wall every time, and which is totally uneconomical, it is very difficult to get a good coating. I talked of I talked of cold wall reactor coating, where an RF is imposed on the area, RF is imposed on the area, and that causes the dissociation. The physical vapor deposited coating, the plasma assisted coating, the atmospheric pressure CVD and the low pressure CVD. These methods are used mainly in the semiconductor industry, but you have to realize that even though it is semiconductor industry, a simple device has a significant amount of ceramics with the extent of 30% or so. So, being able to deposit good non-uniform thin film ceramic coatings is a challenge. If you think that the processes that I have outlined is good enough, unfortunately it is not. You can have these coatings done on your, as I said, my plastic lenses. On there and on those flexi coatings where they put up ads, public ads, and depending on how the coating is done, you will have uniformly thick or thin coatings. The use of these coatings are multifarious. It can be for electrical properties, it can be for any other property. But the most interesting one I showed you yesterday was this one, coating the cloths with titanium dioxide so that the powders could coat the cloth and make it antibacterial. There are many other coating methods, but none of them are still standard in the ceramic industry. Even if you ask me, even the low pressure CVD work, that is also not compatible with what the demand is in ceramics. Before I quit, let me again go back to the solution growth, because solution growth in ceramics is a very important one. Please remember that in solution growth, when we are working, and this is a recap of the lecture, what I had said was initially the droplet was this big, then it becomes this small, then finally very small. Here this droplet is composed of umpteen crystals of the starting material. And when they dissociate all of these materials, each grain dissociates to give you a huge number of nucleation centers. The problem with coatings is that frequently they would nucleate, form large groups, large blobs, and as a result on the surface of the substrate I would get this sort of a distribution of particle size. This would obviously destroy the electrical, mechanical, optical property of any coating. So here what I said is the nucleation and growth of the grains by any process, because fundamentally you are dissociating a compound. During the time of flight, the nuclei should not be in such a position that it can grow very randomly. In that case, if it grows very randomly, then what you can have is this sort of an inhomogeneous coating which serves no purpose. Yesterday, I will finish off by saying what I was talking of yesterday. The Ferrari cars, the top of the line A1 sprint cars. Their beauty is the coating thickness has to be within plus minus 1 micron, and the root mean square surface roughness has to be less than 10 nanometers. Why? so that the drag is reduced. At that temperature, even that small height would cause not only drag, but the airflow pattern would change. So, if I have got a surface where the coating is not uniform, the airflow pattern would simply upturn the car. And the Ferrari, if you happen to ever look at Discovery Channel, they have got an excellent show where they show how Ferraris are coated. They are coated with just a handheld gun, nothing more. So, ceramic coatings, forgetting so many big names, LPCVD, plasma enhanced CVD and all of that, it fundamentally comes down to how you are doing the coating and how you have prepared your powder. Thank you.